Okay, so first I'll mention the main theorems again, which are non-embeddability theorems for specific simple shell complexes. Then we'll go about using the deleted joins to derive the main result. Then we'll take a slight tangent and talk about these nice constructions called biospheres. They'll in fact help in proving one of the main theorems. Then we'll go back and use this main result for using deleted joins to get a non-embeddability result by associating graphs to simple shell complexes. Okay, so let's start. So this is the theorem we have already seen, the topological radon theorem. So I'll just briefly tell it again. If there is a map from sigma d plus 1, which is the d plus 1 dimensional simplex to Rd, then there are two disjoint faces whose images intersect. Okay, and just as Urshita explained, this is the simplest case, t equal to 1. Some vertex and some point on the opposite edge will get identified. That's what this theorem is saying. Now the next theorem is a similar flavor. Here we're considering a map from the d-dimensional skeleton of sigma 2d plus 2 to R2d. Okay, and the assertion is the same, that there are two disjoint faces whose images intersect. Okay, so the D skeleton is just the subcomplex having all simplices having dimension less than equal to D. Okay, so one nice consequence of this theorem is the non-planarity of the complete graph on 5 vertices, K5. And that again is the simplest case of this theorem, taking D equal to 1. You'll get that the one-dimensional skeleton of sigma 4 cannot be embedded in R2. But the one-dimensional skeleton of sigma 4 is just the complete graph on 5 vertices. Okay, so those are the two main theorems. So let's start proving our main result. Okay, so recall what the deleted join was. So for deleted join of K, the simplices are you have two copies of the vertex set of K, and you're supposed to choose one simplex from each copy, but the simplices you choose should be disjoint. And these are some properties that Urshita has proved. The deleted join of the join is the join of the deleted joins, and the deleted join of sigma n is Sn, and hence its Z2 index is n. Okay, so let's start deriving our main result. So this procedure is very similar to that bad map thing that was talked about. So I'll just go through what will happen in this case. So suppose there is a map from K to Rd such that any 2 points with disjoint supports don't get identified. Okay, then from this map, you can get a map from the join of K with itself to the join of Rd with itself, just as what Urshita explained. Just apply F to each coordinate. Okay, then you can check that this map will be continuous. And it is a Z2 map because if you swap X and Y over here, which was the Z2 action for joins, F of X and F of Y will get swapped here. So this is a Z2 map. Now, if you restrict this map to the deleted join, again, obviously the image will be contained in the join of Rd with itself, but it will be points for which this Y1 is not equal to Y2, right? Because the initial assumption said that points with disjoint supports have different images. Okay, so so the image for the deleted join will lie inside this subset of the join of Rd with itself. But instead of considering this subset, we actually consider a slightly larger subset given over here. See here, the points you are removing are for when Y1 is equal to Y2, right? But for this set, basically we are just removing for Y1 is equal to Y2 and T equal to half. So we're removing less, which means that this set is bigger, and hence the image will be contained in this set also. Okay, this makes no difference as we go on because these two spaces happen to have the same Z2 index. And we denote this set as the deleted join of Rd. Okay, and this is just a definition, like you can define it for any space. Just wherever you see Rd, you put X, and then you have a definition for the deleted join of a space X. So what we have finally is a Z2 map from the deleted join of K to the deleted join of Rd. And hence it will give this inequality for the Z2 indices of these spaces. Okay, so it remains to find out what this Z2 index is, and that is given by this. So the lemma states that there is a Z2 map from the deleted join of Rd to Sd, which in turn will mean that the Z2 index is less than equal to D. Okay, so now this is our main result, main non-embeddability result using deleted joins. So if the Z2 index of the deleted join of K is greater than D, then there cannot be a map, right, from K to RD for which any 2 points with disjoint supports don't get identified. Because we know if that happens, then this inequality should happen. But it can't happen because we assume the Z2 index is greater than D. So any map from K to RD will identify some 2 points with disjoint supports. Okay, so this is our main non-embeddability result. It remains to prove this lemma. But before that, we can get the proof of the topological Radon theorem from this result directly. Okay, because, okay, for the topological Radon theorem, what we were interested in was sigma D plus 1, right? So taking K to be sigma D plus 1, by the property of deleted joins, we know that its deleted join will be SD plus 1, whose index is D plus 1, which is greater than D. Then applying this result, we get a proof for the topological Radon theorem, right? So now it remains to prove this lemma, which I'll do now. So to get that the Z2 index of this space is less than or equal to D, we want a Z2 map from the deleted join of RD to SD, right? And the way we'll do that is through the series of Z2 maps. Okay, this last map has already been discussed before, right? From the deleted product of D plus 1 to SD. That was this map. It was already mentioned before. And here B is the D-dimensional open ball. Okay. And we know that RD is homeomorphic to B. And via that homeomorphism, you can get this Z2 map. Remember what I mentioned about deleted join for any space you can define. That's how we get this deleted join of B. So we have this Z2 map and this Z2 map. So what we care about is this one, which we get in this way. So we define two maps from B to the product of RD plus 1 with itself, which is basically just R2D plus 2, right? And this is how you define the two maps. And then using these two maps, we'll combine them to get a map from the deleted join of B to the product of RD plus 1 with itself, which is given over here. Just multiply this by T, multiply this by minus T, and add them both. Okay, and that's how you get the map from the deleted join of to the product of RD plus 1 with itself. And you can check that its image will actually lie in the deleted product of RD plus 1. Because if you have this first D plus 1 equal to the second D plus 1, you'll get T equal to half and X equal to Y. But that is precisely what we removed in the deleted join of B, right? And you can check that it's a Z2 map, right? Because if you swap X and Y, this first D plus 1 and second D plus 1 will get swapped, which will mean you're basically swapping the first and second coordinates in this product. Okay. So we get the Z2 map and hence our lemma and hence our main result. Okay. So another consequence of the main result, apart from topological Radon theorem, is the non-planarity of this bipartite graph K33. Okay, so how do you see that? So first of all, K33 is the join of D3 with itself, where D3 is the discrete space with 3 points. Okay, then just by definition, you can see that the join will be K33. So yeah, and by the way, in all these diagrams and all, when I'm just drawing a line, this is just saying that these two are in the same simplex. This is not a realization of the complex or anything. Okay, so I just wanted to mention that. And then the second thing is that the deleted join of D3 is S1. So how do you get the deleted join? From the join, you have to remove these three lines, right? 1, 1 dash, 2, 2 dash, 3, 3 dash, when you're choosing the same thing from both. And when you do that, you can see that what you're left with is a circle. Okay, so if you rearrange the vertices, you can see it better. It is a circle S1. And then using our properties for join and deleted join. So deleted join of K, you can take the deleted join inside. So you'll get S1 join S1, which we know is S3 by that thing. SM join SM, SN is SM plus N plus 1, right? So the join is S3. And hence the Z2 index of the deleted join of K is 3, which is greater than 2. So by our main result, this K cannot be embedded in R2. That is, K33 is non-planar. So now let's go to this biosphere construction. Okay, now K is a simplicial complex. See, remember that K is just a collection of sets, right? So this is just usual set inclusion. And this is not saying that the vertices, that there are n vertices in K. Okay, this is saying that there are at most n vertices in K. That's all. Okay, just we are considering this subset to be considered. I mean, this simplicial complex to be a subset of this collection of subsets of the numbers from 1 to n. Okay, and when you have such a simplicial complex, you can define the Beer n sphere in this form. Okay, so basically what you're doing These are all the simplices, okay, in the BRN sphere. So again, there are two copies of the numbers from 1 to n. And from the first copy, you have to choose some simplex of k. Okay, and from the second copy, you choose the complement of something that is not in k. And your choices should be such that f is contained in h. I'll leave it to you to verify why this is a simplicial complex. So that is the definition. Let's look at an example to see what this is. So here we're taking k to be the set of all subsets of the numbers from 1 to 2d plus 3, which have less than equal to d plus 1 elements. Okay. And that is actually the d skeleton of sigma 2d plus 2. Right. So this is what we care about in the Van Kampen-Floers theorem. Right. This was the simplicial complex that was there. Now taking n equals 2d plus 3 in this definition, you can define the BN sphere for this k just by plugging in the definition. See, f belongs to k means it has less than equal to d plus 1 element. Similarly, h does not belong to k means greater than d plus 1. So just by definition, you get this. And rewriting these two conditions in terms of the complement, you can write it in this form. But now when you read this definition again, you have actually just written down the deleted join of k. Right, because less than equal to d plus 1 just means it belongs to k. Right, so in this case, the BRN sphere of k is the deleted join of k. It's not true in general, but for this specific k and n, it turns out to be the deleted join. So now why are these things called Beer spheres? Because, well, they're actually spheres. So Beer nk is the n minus 2 dimensional sphere. Okay, so taking this theorem for granted for now, we can use our previous example to get a proof for the Van Kampen-Floers theorem. Okay, so just as before, you take k to be this simplicial complex. And in the previous example, we showed that the deleted join of k is the Beer 2d plus 3 sphere. And by this theorem, that will be the S2d plus 1. Right. And hence the Z2 index of the deleted join is 2d plus 1, which is greater than 2d. And hence by our main result, any map from k to R2d identifies some 2 points with disjoint supports. And hence we have proved our Van Kampen-Floers theorem. So it remains to prove this theorem. So I won't be going through the details that is there in the notes. I'll just give an idea of how the proof goes. So for this trivial simplicial complex, showing that it is Sn minus 2 is just, I mean, you write out the definition and see what it is and all, and then this you can get that it is the n minus 2 sphere. And then the idea is to use induction on the number of simplices. Okay, this is valid because if I give you a simplicial complex and you remove a maximal simplex, okay, what you have left will still be a simplicial complex. Because what do you need for a simplicial complex? Any set you take, all subsets should be there. So if you're throwing out something that is maximal, you're not affecting this property, right? You're not throwing off a subset of something that is still there. So it is valid to use induction on the number of simplices. And then you can show that if I'm getting this simplicial complex by adding f to k, then what I'm essentially doing on the Beer spheres is that I'm retriangulating a ball on the sphere associated to Beer nk. Okay, so some operation like this will be Beer nk, and then I'm retriangulating this ball on the surface of the sphere. And if you retriangulate a ball on the surface of the sphere, what you have left is still a sphere, right? So that's how you will prove this theorem using induction. And such operations where you retriangulate a ball on a sphere is called a bistellar operation. Okay. So, okay, now this is a nice consequence of this Beer sphere construction. I won't go through what the proof is and all. So basically, this is what it is saying. This Beer sphere construction gives so many triangulations of the sphere that it is in fact more than the number of triangulations of simplicial convex polytopes with the same number of vertices. Okay, which in particular will mean that there are some, in fact, many triangulations of spheres for high enough dimensions that cannot be obtained as the boundary of some polytope. Okay, so this I thought was pretty interesting, so I just mentioned it. So now let's go back. We want to get a non-embeddability result for general simplicial complexes using graphs. Okay, so see our main result, to apply our main result, we needed to bound below the Z2 index of the deleted join, right? So this is our goal. We want to get a general way to do this. So first what we'll do is we'll get a general lower bound for the Z2 index of any simplicial complex. And then we'll apply that in particular to our case of interest, the deleted join. and then see how we can reframe that lower bound in terms of graphs. Okay, so what is the idea for the general lower bound? So that is this. Basically, if the simplicial complex has a lot of simplices, then its Z2 index will correspondingly be large. That is, you look at all the subsets of the vertex set, lot of these subsets should be simplices of the simplicial complex. So that is the idea. So how do you formalize this thing? We'll be using this lemma. So L0 is a simplicial Z2 complex. Okay, and I'm partitioning the simplices in L0 into two sets, L1 and L2. And L1 and L2 are closed under the Z2 action. See, what this means is, see, Z2 is a simplicial Z2 complex. So the Z2 action is a simplicial map. It will map simplices to simplices. So what this is saying is that simplices in L1 get mapped again to simplices which are in L1, and similarly for L2. Then in this situation, you get a Z2 map from the space of L0 to the join of these two spaces. Okay, so remember, if I have some collection of sets L, then delta L is the order complex of this poset. So what this means is that the vertices are the non-empty sets in L, and the faces are inclusion chains. Okay, and you can show that the Z2 action on L0 induces a Z2 action on these two spaces. I'll explain what the action is when I'm proving this lemma. Okay, so first we'll get a nice consequence of this lemma, then we'll go to the proof. Now, if suppose this L1, which we'll call L for now, is a simplicial complex, then we denote this delta L by SD of L and call it the subdivision of L, right? And we have proved that these two spaces are homeomorphic. Okay, and also remember that we have this bound for the Z2 index of a join. Okay, so using these 2 points and applying it to this lemma, we get this theorem called Sarkaria's inequality. Okay, so basically this is saying, suppose L1 you write as L is not just some subset, but in fact a subcomplex. Okay, then this L2 is just L0 minus L, right? Because it's a partition. Then using the bound on the join and jumbling the terms around and all, you get this inequality. Okay, and you replace delta L by L because we know the sub for the, if L is a subcomplex, then those two spaces are homeomorphic. So we have this inequality. And how we use this inequality is we'll start with some simplicial complex L. Okay, and we want to choose some L0, a simplicial Z2 complex that contains L, for which we know something about the Z2 index. And ideally, we want to add very few extra simplices to get L0 from L, so that you'll know something about this, and this will be very small. Okay, so that is our ideal situation for applying this inequality. Okay, then we'll get a lower bound, right, on the Z2 index of L. And this is the general lower bound, which I was mentioning. Okay, so it remains to prove this lemma, which I'll do now. Okay, so to get this Z2 map, we'll consider L0. We'll consider the triangulation of L0 given by the subdivision of L0. Okay, so remember the vertex set is the non-empty simplices and the faces are just inclusion chains. And the Z2 action on L0 is a simplicial map, right? So it maps simplices to simplices. So in particular, vertices of the subdivision get mapped to vertices. And you can show that that map will be also a Z2 map on SD of L0, and they'll be homeomorphic Z2 spaces. Okay, so when we look at L0 in this way, what we essentially want is a Z2 map from this space to this space, right? And the Z2 map is fairly straightforward. Start with a vertex here. That is just some simplex of L0, right? Non-empty simplex of L0. And the vertices in this space is just non-empty sets in L1 and then one copy of non-empty sets in L2. But since L1 and L2 partition L0, that is basically you have one copy of each non-empty set, non-empty simplex of L0. So just send it to wherever it is. This comma 1, comma 2 is just indicating into which set of vertices I'm sending it to. Basically just send it to the same simplex. Okay, and then you can show this is a simplicial Z2 map, because if you start with the chain in L0, you'll just split up into a chain in L1 and a chain in L2. And that will be a simplex in this join, right? And you can show that it is a Z2 map because of how we have defined the Z2 actions. The Z2 actions on delta L1 and delta L2 are just like how you defined it on the subdivision, because L1 and L2 are closed under the Z2 action of L0, right? And you can check that it is just the same. It is a Z2 map. So now we have, with the proof of that lemma, we have Sarkaria's inequality. And our goal is to use Sarkaria's inequality to get a lower bound for the Z2 index of the deleted join. But before going to that, I just want to mention that you can get a proof of the Van Kampen-Flo's theorem directly from this inequality. I'm not going to go through the steps. It's there in Matasek's book. But essentially, what you do here is what we are going to do in general for this specific case. So I thought we might as well just do the general one. Okay, so let's go to a case of interest, the deleted join. So in Sarkaria's inequality, which is this thing, we want to put L equal to deleted join of K, right, to use our non-embeddability. So the question is, what will you choose as L naught? Now, if K has n vertices, that means K is a subcomplex of sigma n minus 1, right? So in particular, the deleted join of K is a subcomplex of the deleted join of sigma n minus 1. And that is what we'll choose as L naught. Because we know this thing Z2 index is n minus 1. Because this is Sn minus 1, right? So we know this Z2 index. And so applying Sarkaria's inequality, our objective has turned to bounding this Z2 index above. Okay, so this looks more complicated, but now with coming lemma, our result will be over. Okay, so this is the lemma. So the same situation as before. K has n vertices, and this was the thing we wanted to bound above. And this lemma is saying that this chromatic number of gk minus 1 is the upper bound. Okay, so this gk is a graph which you'll associate to a complex k. Okay, I'll define how to associate graphs to complexes in some time, but before that, I just want to get our main result. And chromatic number is just the minimum number of colors you need to color all the vertices so that any two adjacent edges have different colors. I mean, any two adjacent vertices have different colors. Okay, and then this inequality is just plugging in n minus 1 over here. You get this inequality. Now, into this inequality, if we substitute this bound, that is replace this by minus chromatic number plus 1, then you get this bound, this lower bound. Okay, and this theorem is called Sarkaria's coloring theorem. So the Z2 index of the deleted join is bounded below by this quantity. Okay, and so using our main result, if this quantity is strictly greater than D, that is D is less than equal to this quantity, then by our main result, K cannot be embedded in R2, right? I mean, 2 points with disjoint supports get identified. Okay, so this was the theorem that uses graphs to get non-embeddability, but it still remains to define what this GK is and then prove this lemma, which I'll do now. So K is a simplicial complex. We want to know what GK is. So V is the vertex set. Now the vertex set of this graph GK is the set FK, which is the inclusion minimal sets in this collection of sets, which is basically all the subsets of the vertex set, which are not simplices. Okay, so the minimal non-faces of K. That is the vertex set of GK. And then there's an edge between any two such sets if they are disjoint. Okay, so let's look at an example to see what this is saying. So we look at again, the bipartite graph K33. So this is how we represented it. Now you can check that these 6 are the minimal non-faces. Okay, they are surely non-faces because there is no edge between any two undashed or any two dashed numbers. And you can verify that these are the only minimal non-faces. And any two here will intersect, right? Because they are two subsets of a 3 set. And similarly here, any two will intersect. But anything from this side won't intersect anything from this side. So you have to draw an edge because they are disjoint. Okay, in this example, it turns out GK is the same as K33, but that's not true in general. In fact, you can show that for any KNN, if you want GK to be equal to KNN, that will only happen if n is equal to 3. So I'll leave you to verify that. So now this is basically how you get GK from the simplicial complex K. And now we have to prove the lemma, which was saying that this thing Z2 index is less than equal to chromatic number minus 1. So, I mean, let the chromatic number be n, and let's, okay, so by the definition of what GK is and what a proper coloring is, this just means that for any two minimal non-faces, the colors are different if they are disjoint. Okay, and then just representing this simplicial complex by L0 and this by L, what we need is a Z2 map from delta L0 minus L to Sm minus 1, because we want its index to be less than equal to m minus 1. And the triangulation for Sm minus 1 we'll use is this. Okay, because we are concerned about sets and disjointness and all, this will be a very convenient triangulation. Okay. So now the vertex set of this complex is just the non-empty sets in L naught minus L, right? And remembering what the definition of L naught is and L is and all, you can see that this is the vertex set. Okay. That is, there are again two copies of N. You have to choose a disjoint copies from each, and at least one should not be in K because you don't want it to be an element of the deleted join of K. Okay, and similarly, the vertex set of, I wrote Sm minus 1, but actually I'm talking about this triangulation. Similarly, again, from definitions, you can show that it is just, there are two copies of M. You have to choose two disjoint things from each copy, and at least one of them should be non-empty. Okay, so you can just check that these two are the vertex sets. And the Z2 action is just swapping these two. Okay, so that is the Z2 action, and the simplices are just inclusion chains. Okay, so now we want a simplicial Z2 map from delta L0 minus L to Sm minus 1, and we define it like this. Okay, so it remains to say what is H. Okay, so H of F is all the colors for any minimal face sitting inside F. Okay, so first of all, why is this map well defined? So if I start with some vertex here, at least one of them is not in K, right? So that means at least one of these is a non-face, which means one of these will contain a minimal non-face, right? So that means at least one of these H things has to be non-empty because at least one of them will contain a non-face. So the non-empty part is fine. And the disjoint part is because this C is a proper color. Because these two are disjoint by definition, these two are disjoint. So if I have two minimal non-faces sitting inside them, they'll also be disjoint and the colors will be different. So like that, you can show that this is well defined. And it is obviously Z2, you swap these two get swapped. And it is simplicial when you prove that H is, it preserves inclusions. So then chains will get mapped to chains. So that will prove the lemma and hence the coloring theorem. And this was the non-embeddability part of Sarkaria's coloring theorem. If I have a complex with n vertices, and if B is less than equal to n minus chromatic number of GK minus 2, then K cannot be embedded in RB. This was the final part of Sarkaria's coloring theorem. And so we'll prove VKF using this. Okay, so again, just take K to be this simplicial complex. And Fk, remember, is the minimal non-faces. Okay, so anything with D plus 2 elements, exactly. That is a non-face, and every subset of it is a face, right? And you can see that these are the minimal non-faces. Anything with more than D plus 2 will have some D plus 2 subset. So these are the minimal non-faces, but any two minimal non-faces will intersect because there are only 2D plus 3 terms, and D plus 2 plus D plus 2 is 2D plus 4. So that means any two minimal non-faces will intersect, which means there are no disjoint ones, which means there are no edges in GK. And hence GK's chromatic number is 1, because if there are no edges, just color everything one color and it's fine. And so plugging in everything here, n is 2D plus 3, the chromatic number is 1 and minus 2. You'll see that 2D is less than equal to this. And hence by this result, we'll get a proof for the Van Kampen-Floers theorem. Okay, so that is it basically, but I just wanted to mention these few results. So we talked about for higher dimensions, there are many spheres that cannot be triangulated by convex polytopes. But in fact, for S2, every triangulation is polytopic, which maybe, at least I found it difficult to see why that theorem, why that result is actually true, because mostly we'll imagine in S2, right? So in fact, for S2, all triangulations are polytopic. And the non-embeddability of the real projective plane in R3 can be shown using our deleted join methods. This is given in Math's textbook. It's an example in 5.8. And we use Sarkaria's coloring theorem to get a lower bound for the Z2 index of the deleted joint using a graph. But in fact, you can flip this on its head and use it to get a lower bound for the chromatic number using Z2 index of a graph. Okay, so because essentially you can show that actually these are lower bounds for certain graphs called Nezer graphs. But in fact, every graph is a Nezer graph. So this is a bound for all graphs. Yeah, so that's it.
Krishna, in what sense you mean every graph is a Nezer graph?
Yeah, you start with a graph. You can find a corresponding set whose Nezer graph, a collection of sets whose Nezer graph is the graph you started with. It's not very easy to apply this lower bound.
Nezer graph has a particular definition. Like, for example, let's say I start with a cycle graph. Cycle graph means Just you start with a cycle and throw in vertices somewhere. So this looks like a n cycle, which has n vertices and n edges. So can you tell me it is Kinesa graph for what values of what parameters?
Oh no, I mean the definition for Nesser graph in Matusek's book is like you are given a set system,
Mm-hmm.
and it's like how we define the graph associated to a complex, right? So in that set system, the vertices are the set system, and there is an edge between any two sets if they are disjoint.
I know.
So you want me to give a proof that every graph is a Nesser graph?
Yeah, I mean, it's hard for me to see that.
Yeah. So actually, there is one more concept called intersection graphs, where like it's the same thing, but you join two sets if they intersect instead of the just disjoint condition.
They are
So,
actually called generalized Kinesa graphs.
oh, okay. So essentially, I mean, I don't have any writing, I mean, tool or anything. So shall I just use Paint and
Yeah, either
I
is
don't know.
fine. Either is fine. Or you can just, if at all you have any sort of algorithm in your head, how given any graph you will go about finding a number n. So, okay, so for rest of the people who do not know what a Kinesa graph is, because this would have come in next 2 lectures of mine. I mean, they are there with me, but they haven't gone online. So, Kinesa graph means that you start, let's say, some n elements, okay, and then there is a number which you fix, let's say k. So now you start looking at k subsets of n, subsets of size k coming from these n elements. So these subsets form the vertex set for this graph, and now two of these vertices are adjacent if the corresponding subsets are disjoint. Am I clear to everyone? Since everybody's video is also off, I can't really see if...
Yeah, it was clear.
Yeah.
Yeah. So, uh, so then now the question in picture right now is that if you have any graph, can you find the parameter n and k? So Kneser graph is generally denoted as kg, capital K, Kneser,
Magkano?
capital G,
Wala
graph.
na yulo. Niya yung kariyera yun, no? Pag malang discuss yun, yun.
Huh?
Deepak, your mic is on.
So kg and k is the notation for a Kneser graph where elements are k subsets of whose vertices are k subsets of a set n. So the question that I'm asking Krishna right now is that can you, given a graph G, can you always find parameters n and k such that kg and k is isomorphic to G?
Yeah. So this was the first. I mean, when I read that section about the Nesser graphs, this was the first example. I mean, someone raised some question or something, and he was talking about these types of Nesser graphs. But then he gave a more general definition. Like you're just given a collection of sets. Okay, some collection of sets you are given, and just as before, the vertex set of the graph is these sets, and so there is no condition like each of them should have k elements. So that condition is dropped. So they are just sets, any old sets. I mean, finite sets. They're just any sets, and there's an edge between two such sets if they are disjoint. So it is the same thing, but just the condition, the k condition is dropped. It's not like each set should have exactly k elements.